In this lesson, you'll learn about propellers, their function and operation. Although we will, of necessity, very occasionally make mention of the aerodynamics of propellers, it is important you be aware that this is not a lesson on the aerodynamics of propellers. Propeller aerodynamics are dealt with in the subject Principles of Flight. The purpose of a propeller is to provide thrust to drive the aircraft forwards through the air. This is achieved by accelerating a comparatively large mass of air rearwards, thereby producing forward thrust. A propeller consists of two or more aerodynamically shaped blades attached to a central hub. This hub is mounted onto a propeller shaft which is driven, either directly or indirectly, by the engine. The hub and the blades are thus spun round by the propeller shaft, and act rather like wings, which by rotating would generate lift, or in this case, thrust. In order to be able to explain how a propeller works, it's necessary that we use a certain amount of terminology. Like a wing, a propeller blade has a root and a tip, a leading and trailing edge, and a cambered cross-section, whose chord line passes from the center of the leading edge radius to the trailing edge. The cambered side of the blade is called the back, while the undercambered side is termed the thrust face. Where the section of the blade becomes round at the root area is termed the blade shank, while the base of the blade is called the blade butt. The propeller blade is set into its hub so that its chord line forms an angle with the plane of rotation of the whole propeller. This is called either the pitch or blade angle. The theoretical distance, ignoring slippage, that a propeller or propeller blade moves forwards when the propeller shaft has completed one rotation is called the geometric pitch. All propellers, however, lose a certain amount of efficiency due to aerodynamic and compressibility losses. As a result, the geometric pitch can never be achieved. The actual distance that the propeller moves forward during one revolution is called the effective pitch. The efficiency loss, that is, the difference between geometric pitch and effective pitch, is known as slip. The efficiency achieved will usually be in the range of 80 to 90%, and can be found by using this formula. The path of the propeller blade through the air, which describes a helix, determines the direction from which it will receive its relative airflow. This helical path is the resultant of the propeller blade rotational velocity and the aircraft forward velocity. The angle between the relative airflow, the actual path the blade describes through the air, and the chord line of the blade is called the angle of attack. The angle of attack is kept quite small, usually between 2 to 4 degrees. As the blade rotates at this small, positive angle of attack, a thrust force is generated, very similar to the way in which lift is generated on a wing. Because the rotational velocity of any point on a propeller blade increases with increasing distance from the center of the hub, so the magnitude of the thrust generated at any point along the blade would also increase with this distance, if the pitch of the blade remained constant along its entire length. If the blade pitch remained constant along the length of the propeller blade, the increase in force developed by the outer part of the blade, compared with that developed at the slower-moving blade root, would tend to bend the blade as depicted here. The angle of attack depends on blade angle, the rotational speed of the propeller, and the forward speed of the aircraft. To keep the angle of attack within necessary limits along the length of the blade, we therefore reduce the blade pitch from root to tip. This has the effect, when the aircraft is in flight, with the propeller rotating at its designed operating RPM, of maintaining a fairly constant thrust force along the length of the blade. We've just seen that a propeller receives its relative airflow from a direction which is governed by the aircraft's true airspeed in the direction of flight, and its own rotational velocity in the plane of rotation. The operating angle of attack will be the angle between the relative airflow and the chord line of the propeller blade. This chord line is set at an angle to the plane of rotation, which, as we've already seen, forms the blade angle or the propeller pitch. From this animation, it can be seen that an increase in true airspeed will reduce the angle of attack, whereas an increase in rotational velocity, or RPM, will increase it. At high true airspeed and low propeller RPM, for instance with the aircraft in a power-off dive, it's possible to reduce the angle of attack to 0. While at low true airspeed and high RPM, for instance in the climb, it's possible to stall the propeller blade. Both extremes are obviously inefficient and therefore undesirable. The conclusion that must be drawn is that for a given fixed pitch, a propeller will only work efficiently at one combination of true airspeed and RPM, as is shown in this diagram. The propeller designer will attempt to ensure that peak efficiency is achieved at cruise true airspeed and cruise RPM. When a fixed-pitch propeller is being driven by a piston engine, the RPM is dependent on both the power setting, throttle position, selected by the pilot, and the true airspeed of the aircraft. It would be possible to overspeed the engine in a dive if the throttle was not closed. Conversely, with the aircraft stationary on the ground, it may not be possible to achieve rated RPM with the throttle fully open. Because of all of the disadvantages of the fixed-pitch propeller that we have just mentioned, advanced piston engine aircraft are fitted with variable pitch, constant speed propellers. This type of propeller is able to operate efficiently over a wide range of airspeeds. The power setting of a piston engine is defined by a combination of manifold pressure and engine RPM. Where both a separate power lever and a propeller RPM control are provided, it's possible to vary one of these parameters while leaving the other to remain constant, so optimizing the operation of the engine-propeller combination to give the best efficiency and fuel economy, while reducing the engine wear and tear to a minimum. In order to achieve this, a variable pitch propeller is used. The system changes the pitch angle of the propeller blade to vary the load on the engine, thereby maintaining the selected RPM of the engine-propeller combination independent of manifold pressure, provided that the propeller is operating between its fine and coarse pitch stops. The fine and coarse pitch stops may be fitted internally or externally, depending on the make of the propeller. Once an RPM has been selected, a control unit, either a constant speed unit or propeller control unit, will automatically vary the propeller blade pitch angle, and therefore its angle of attack to the prevailing relative airflow, in order to maintain the selected RPM despite variations in airspeed and manifold pressure. Variable pitch propellers may also have a reverse pitch and/or feathering function, the advantages of which will be discussed later in this lesson. This animation shows that under normal propeller control conditions, it's possible to provide a range of propeller pitch angles ranging from max coarse, cruise, all the way through to reverse pitch. The alpha, or constant speed range, is used for normal flight. It includes all pitch angles from flight fine through to max coarse, while the beta, or ground range, includes pitch angles between flight fine and maximum reverse. The feather position is not included in either range, and is used for emergency conditions only. In the event of engine failure, the propeller blades will be moved directly to this position to prevent windmilling. There are no pitch angles available between max coarse and feather. The method of control within the alpha and beta ranges, and the means of achieving the propeller feather position, will be discussed progressively throughout this lesson. Varying the pitch of a propeller throws up two basic problems, one of blade actuation and one of pitch control. We will initially examine the problem of blade actuation. The issue of pitch control will be covered later in this lesson. Although mechanically or electrically actuated pitch change mechanisms are in use, the hydraulic method is the most commonly used. The system utilizes oil from the engine or reduction gearbox lubrication system as the source of hydraulic pressure. In this system, the pitch change mechanism is operated by a piston moving under the influence of the oil pressure. Use the up and down arrows on your keyboard to change the pitch of the blades on this propeller. Hydraulic pitch change mechanisms can be one of two types, single-acting or double-acting. A single-acting propeller has oil pressure applied to only one side of the piston. The return movement of the piston requires the force of a spring, or sometimes compressed gas. A double-acting propeller has oil pressure applied to either side of the piston, in order to move the propeller between the two extremes of fine and coarse pitch. Whichever type is used, the flow of oil to and from the actuating piston is controlled by a propeller governor. Dependent on the propeller manufacturer, the governor may also be known as a constant speed unit or propeller control unit. In addition to controlling the propeller pitch angle, the unit normally incorporates a small oil pump, which increases the oil pressure to the value required for system operation. A single-acting propeller is constructed basically like any other variable pitch propeller, in that the blades are arranged round a central, engine-driven hub with the cylindrical hydraulic pitch change mechanism mounted at the front. The pitch change cylinder, or dome, contains a movable piston which is activated by boosted engine oil pressure. Movement of the piston will rotate the propeller blades towards either coarse or fine pitch. Typically, rotation is accomplished by a mechanical linkage attached to the rear of the piston, which operates an actuating pin machined on the butt of each blade. The actuating pin is offset, in order that it can impart the correct range of angular motion. Generally, blade rotation towards coarse pitch is induced by an internal spring or gas pressure, and or counterweights attached to the blade roots. Most single-acting propellers, however, will utilize both a spring and counterweights. As we said earlier, some systems may use compressed gas instead of the spring. In feathering-type propellers, the spring has a dual function. It assists the counterweights in driving the propeller blades towards coarse pitch, and, when selected by the pilot, it actuates the blades into the feathered position, when engine RPM is low and there is insufficient centrifugal force acting on the counterweights. The constant speed unit, or CSU, incorporates a valve, which, because it has lands or grooves cut into the operating portion of its stem, is called a landed valve. This landed valve controls the flow of oil to and from the propeller actuating, or pitch change cylinder. A speeder spring, acting above the valve, tends to force the valve downwards, while a set of flyweights, driven by the engine, oppose the spring and act to lift the valve. An input from the pilot's RPM lever, or propeller condition lever, will adjust the setting of the speeder spring, selecting the RPM, which the CSU then automatically maintains. In order that it can respond to the various demands made by the pilot regarding the propeller RPM, the constant speed unit controls the oil flow to the pitch change cylinder in three ways. If the propeller is underspeeding, then the flyweights will be leaning inwards because of the reduced centrifugal force, allowing the speeder spring to push the landed valve downwards. This will allow the unit to supply oil to fine off the pitch of the propeller, causing an RPM increase. If the RPM is as required, in other words the propeller is on speed, then a hydraulic lock is formed in the system, maintaining the blade pitch constant. If the propeller is overspeeding, then the flyweights will be forced outwards by centrifugal force, compressing the speeder spring and allowing the landed valve to move upwards. This will allow oil to drain back into the engine system as the piston is moved under the force of the spring, coarsening the blade pitch, causing an RPM decrease.